All right, I have mentioned briefly that there is a fourth quantum number that we worry about for electrons, m sub s, and the reason for that is that we're now going to talk about multi-electron atoms. All right, so we've talked about hydrogen already, which has one electron and one proton, usually, if it's neutral. But every other neutral atom on the periodic table has more than one electron, and so we have to worry about the interaction between the two electrons. All right, so we have the Pauli exclusion principle applies to multi-electron systems, which says that two electrons in the same atom cannot have the same four quantum numbers. Okay, so they can have three quantum numbers the same, but they can't have all four quantum numbers the same. That would violate the Pauli exclusion principle. So if you have the first three quantum numbers the same n level, same L, and the same m sub L, you have a single orbital, and let's say it's a s orbital. And this, I wrote a 1s orbital. It could be any s orbital. And if you have more than one electron in it, then if they already have the same n level, and they already have the same L level, and they're in the same m sub L level, which there's only one of for an s orbital, then they cannot have the same spin, because they can't have all four the same. So one electron would have to be m sub s equals plus 1/2, and the other electron would have to be m sub s equals minus 1/2. They cannot have the same. And as a result, each orbital is full with two electrons, because there only can be two values of m sub L. So each orbital is full with two electrons. You can only have two electrons in any given orbital, any given m sub L level. All right, and because when there's more than one electron in the system, there's some shielding that goes on, and there is a separation according to the shapes of the different orbitals. The s, the p, the d are treated differently in energy when you have more than one electron. Okay, that's because of shielding. That's because one electron makes the other electron not feel the positive charge in the nucleus as much. They each shield the other one somewhat from the nucleus. Okay, so as a result, in a hydrogen atom or any one electron system, you have, for a given n value, this is n equals 3, you have a 3s orbital, you have 3p orbitals, and you have 5 3d orbitals, but they're all at the same energy. There's only one electron, there's no shielding. There's no other electron to be shielded. Okay, so all three types, and any others as well, any types of different L values all have the exact same energy. Here's the energy scale. Okay, but as soon as you have more than one electron, whether it's 2, 3, 4, or 80, those levels are going to be different in energy. The 3s will always be the lowest energy, the 3p will be higher, and the 3d will be higher. They separate according to L value. The higher the L, the higher the energy. Okay, and this is just an example for n equals 3. It applies to all systems. And when energy levels are all at the same energy, we say they are degenerate, which means at the same energy. Okay, so using these ideas, we're going to be able to build up the periodic table, which we said was consistent with quantum mechanics, one electron at a time. Okay, and to do this, we're going to have a few rules. So we're going to build a periodic table. The first rule is called the Aufbau principle, and it says that each electron added, so as we go along the periodic table, we are basically adding one electron, right? Hydrogen has 1, helium has 2, lithium has 3, etc. So we're going to build up one atom at a time with an additional electron. And each electron added to is added to the lowest energy level available. And that is for a ground state. Remember, we talked about excited states, which might have higher energy levels, but when we're trying to build up a periodic table, we're going to work with the ground state. So the Aufbau principle says each new electron goes to the lowest available energy level. All right, we already said the Pauli exclusion principle, which was that each orbital holds, another way of wording it, each orbital holds 2 electrons of opposite spin. Okay, and the way we're going to designate an energy level is just with a line, and the way we will designate spin is with one arrow going up is an electron with m sub s equals plus 1/2, and an arrow going down is m sub s equals minus 1/2. So I'll write that. All right, and then the third rule is called Hund's rule. And it says if multiple energy levels exist at the same energy, then the electrons will stay unpaired as long as they can. So if multiple levels exist at the same energy, and that's like a p orbital with 3 at the same energy, the electrons will stay unpaired if they can, basically. All right, and okay, so if you have, let's say, 3 p orbitals with 3 different m sub l's, and you had 3 electrons, they would try to stay unpaired. One would go in one orbital, one would go in another, and the third one would go in another. They would not pair up. Okay, they would not go like this. Okay, that's not what they would do. They would fill up different levels, and they would actually, and the spins would also stay parallel. Spins parallel as long as possible. Okay, and the Hund's rule is sometimes referred to as the bus seat rule. When people who don't know each other get in a bus, they will always fill up one person in each seat until they have to pair up, and they'll pair up when they have to, but they will try not to pair up until they have to. All right, and then a couple of conventions. When we draw the electrons, we always start with a up arrow, and then we when we pair them up, then we put the down arrow. And we always, if we have like a p orbital with degenerate levels, we always start on the left, not somewhere else, the middle or the right. And when we label them with m sub l's, we always start from the left with the most negative and go to the positive. So those are just conventions in how we label. All right, so let's start talking about atoms on the periodic table. We'll start with hydrogen. Okay, hydrogen has 1 proton, and when it's neutral, it has 1 electron. So we're going to use the Aufbau principle, which says we put it in the lowest energy level possible. We put it in a 1s. Okay, so I only drew up to 2p. I drew the n equals 1 levels, and I drew the n equals 2 levels. And that's all I've drawn so far. All right, there's 1 electron, so it goes in the lowest level. And remember, these split, although technically with 1 electron they would not split. The 2 levels would not split. Okay, for helium we have 2 electrons. The Aufbau principle says we put 1 there, and Aufbau principle says we got to put the other one here. Okay, we always fill the lowest energy possible. 3 electrons for lithium. We put 1 here, and then the third electron can't go in the 1s because it only holds 2. It has to jump up. Using the Aufbau principle, it goes to the next lowest energy level. All right, and then we write electron configurations for these in shorthand. This is kind of a longhand way of writing it. So we write a shorthand. For this one, we write 1s, and we use a superscript 1 to say that there's 1 electron in it. For helium, it would be 1s2. Okay, that's not squared. It's just 1s2. It's got a 1s orbital, and it's got 2 electrons in it. For lithium, we would say 1s2 and 2s1. 1 electron in the 2s, 2 electrons in the 1s. Let's go on. Let's do more atoms. Beryllium has 4 electrons. 1, 2, we start the same. Do just like we did for lithium. The 4th one, because of Aufbau, has to go in this energy level. And because of Pauli exclusion principle, the spin would be, the last electron would be down. Okay, what's the electron configuration? 1s2, 2s2. Boron has 5. 1, 2, 3, 4, and the 5th one is going to go in the 2p orbital. By convention, we put in the left side, and by convention, we put the arrow up. So the electron configuration for boron, 1s2, 2s2, 2p. How many electrons? 1. So 1 electron in the 2p. Let's do carbon. 6 electrons. 1, 2, 3, 4, 5. Okay, we need 1 more. Where is it going to go? Is it going to pair up with this one? No, this is where Hund's rule finally comes in. And the next electron would stay unpaired as long as possible, the bus seat rule. So it would go in the next orbital over, and it would be parallel spins, they'd both be up. Okay, so now it's your turn. Try one for oxygen with 8 electrons. All right, let's draw the orbitals. 1s, 2s, 2p, and we'll occupy it with 8. 1, 2, 3, 4, 5, 6, 7. That's Hund's rule. Fill them all with 1 electron first. We have 1 more electron though, so we need to start pairing now. We have to, by Aufbau principle, we're going to stay in the lowest energy level possible, and we have to start pairing, so we pair. Electron configuration is 1s2, 2s2, 2p, and how many electrons are there? There are 4. And then the question asks how many unpaired electrons. Okay, these 2 are paired, these 2 are paired, these 2 are paired, but these 2 are not paired. So we say there are 2 unpaired electrons.